So perhaps let's see.
So I stop. Yeah.
Wait, just 1 second, please.
Okay.
So our next speaker, Leonid Fel from Technion, who will speak about symmetric polynomials. Please, Leonid.
Thank you, organizers, for inviting me here and to participate in such an important venue in the number 7 conferences. My talk is commutative monoid of self-dual symmetric polynomials, and I start with motivation of this work. And in 64, Joseph Keller, studying this harmonic potential in the infinite piecewise continuous plane with regular tessellation of different constituents, arrived into the very important algebraic functional equation for the homogeneous function lambda x1, x2 of degree 1, which is invariant under the exchange variables, and it looks very nicely in 1. This equation is so important in theoretical physics in the mass. It gives rise to the so-called percolation theory, and has a very important influence in the theoretical physics, at least. I have come to this problem 20 years ago when studying the percolation in non-equal constituent, for example, not 50 on 50 of in different ratios, and it is very equivalent to this equidistribution of the n component. And very shortly, we have proved with David Bergman from Tel Aviv University that in case of n constituents, the generalized kind of this duality equation looks like in 2. It was astonished me because the equation 1 has exact solution. It does not depend on any distribution of the tiles in the plane, I'd say, from the physical point of view. In a moment, I will show you what is a solution of this functional equation 1. On the other side, equation 2 has not universal solution. So it was a challenge to understand how to deal with this equation 2, and here comes the motivation. What kind of the multivariate polynomials which are invariant under the action of the symmetric group S on the set x1 up to the xn give rise to the root lambda of this variable satisfying equation 2, and what algebraic structures do such polynomial exhibit. I start recalling this so-called self-dual univariate polynomial, for example, following this Joe Andrews in this book of 76. We will distinguish 2 kinds of this univariate polynomial, self-reciprocal and skew reciprocal, that are written here and here, and they both satisfy the duality relation and looks in 3. So this function has very nice algebraic properties. I will not discuss them now. Somewhere in 20 minutes, I will come to tell how they be generalized in the many-dimensional case. And now I pass exactly to this multivariate self-dual. So elementary polynomial invariance in the symmetric group Sn acting on the Euclidean space over the field R read in 4. It is 1 sum of the pairs and so on. And now we go to build this two monic polynomial in lambda of degree mn, where m and n are the natural numbers. N is attributed to the univariate, so I will always presume that n is larger than 1, and they are mimics like as a univariate sum and minus of the sum. Now, what is written here? So the coefficient here presented like the sum of the composition of the invariant in some powers. The brackets has not to confuse you. Simply here I put all these variables that R depends on. So lambda, this is a variable lambda which is depends on all this x1 and xn. M is a number, integer number. Sn remind you that it's invariant under the symmetric group, and xn, this is a tuple, is given here. So this is a short presentation of this. Now, what is the summation? Summation is running over L from 1 up to this PMN. PMN denotes a partition number with constraints. What means the constraints? It means we look simultaneously on the two Diophantine equation. The first one is the second one. And this tells us that we will encounter with a Gaussian polynomial. But in the meantime, I will go by the self. Now, this is a self reciprocal, and this is a skew reciprocal polynomial. Now, here the coefficient R, what is important, here and here are the same coefficient. They are real, and I presume that they are independent. So polynomial R and Rs are called generic if all these coefficients are independent respectively. I give you some example of the generic self-dual polynomials with small m and n. Skew reciprocal with m equal 1 and n equal 2 has no free coefficient. So this is simply lambda square minus x1, x2, self-reciprocal with m equal 1 and equal 2. Lambda square plus any coefficient a, for example, times in brackets x1 plus x2 brackets close lambda plus x1, x2, and so on. You can see that with growing m and n, a number of this free coefficient from the independent coefficient slowly is going. In a moment, I will tell you why the study of this number is important. In the middle, you can see, for example, here, you can see that in the middle, for example, for this 4 and for this, for n equals 3, we have cube, square, the first and 0th degree, and also for the self. But going to the second one, here we can lose, for example, the 3rd degree. You can see, and this m equal 2, n equals 3, we have 6, 5th, 4th. Here, 3rd is vanished, 2nd linear, and 3. So the difference between the skew and self-reciprocal goes in the middle of this polynomial, and sometimes the middle terms in this skew reciprocal can be vanished. By the way, S star, I have, I have denoted that Mn over 2, integer part. Now, what terms are vanishing in this skew reciprocal? They have to satisfy not only the two Diophantine equation, like for this general case, but also for the additional equalities in this degrees. So we go to call the partition number satisfying two equation 8 and 9 by the UMN of S. Now, shortly about these partition numbers. This is very distinguished partition number PMN that comes from the Gaussian polynomials that go back to the Sylvester and Shaw. This is the generating function, and these are the Gaussian polynomials. There are not a lot known about these polynomials. In fact, all this information is given in the book of George Andrews. So they are symmetric under this middle of the from 0 up to Mn. The sequence is unimodal, but not always log concave. There are different proofs of this fact. And the last one was combinatorial by Katia O'Hara. Partition number in the middle satisfies this inequality. In special cases 1 and 2, we can calculate them. For the larger, there are several attempts to give the general formula, but in the meantime, it's not clear how to use simple formulas. That very, very hard to use it. And instead, we have put the conjecture based on the vast number of numerical calculation. And here is conjecture. If we have two M1 and M2, and both of them are modular 2 equals 0 with M1n and M2n. So for n larger than 2, we have to have such inequality. I have discussed this stuff with George Andrews. He said that it is very interesting, but he has not known about this fact. Well, the partition number U is much easy to handle, and we can calculate it exactly. I will not go into the detail, and here are the formula for this partition number with vanishing middle terms. Now, unimodality numbers. The number of coefficients R and S, not necessarily independent, which appeared in self-dual polynomial R and S, are called unimodality numbers and denoted as follows: mu of R and mu of S respectively. And here I give the table of the growing unimodality numbers for the generic. I mean generic. The coefficient does not, they are independent in both sets, and they are growing. Definitely you can verify this conjecture for the very, very high Mn. It is very nice that you can calculate also in general case the unimodality numbers of self-dual polynomials. In the case Mn equal 1 modulo 2 is simple results. Here are a little bit problematic because about PM we don't know a lot. Here are different properties. Now, the unimodality number mu of generic polynomial R and S with fixed M and N exceed, definitely it has to exceed such numbers for the non-generic. Why for the non-generic? Because they are independent. So for the non-generic, unimodality numbers are always less than in the generic case. And now I came to the duality relation of self-dual polynomial. Let us look on this polynomial H. This is invariant under the action of the group Sn, and I will define this transformation Qn on the polynomial H, which is acts by inversion on variables lambda and xi, every xi, in such a way. So QH in inverse lambda and x, and the x minus n I understand in such a way, and invariant are here. So the first theorem tells us that in the presentation that we give in the 5, 6, and 7, in the second page of this talk, the both polynomial satisfy the relation. There are very, very mimics the univariate self-dual polynomials. So it's simply labels us that we are on this, on the correct way, at least. Now, let us define this set of all the self-reciprocal and skew reciprocal polynomial with different set of the parameters as a R bold and S bold. And H we represent in the following way, not presuming that they are satisfied the duality relation. So definitely what we have seen in the definition of the self-reciprocal and skew reciprocal, they are in the set of the all H polynomial. But what is interesting, it is also through the inverse statement. A monic polynomial H, which is given in 18, is self-reciprocal if it satisfies the duality relation in the first line, and is skew reciprocal in the other way. So to have the H self-dual, we have to require that this polynomials has to be has to satisfy the duality relation, and it's correct the opposite statement. Let us define the union of all the sets of R. Look, here's disappeared the M with different M, like this mathematical R and mathematical S. Obviously, this of the all the sets of the skew reciprocal, and the union of them we go to call the RS facts. I don't remember how it's called in mass frac. Yeah. And what is nice, we came to the following statement. First of all, in this set, we cannot define the binary operation like the addition. So the linear combination of self-dual is not self-dual. But the containment about this products works very well. So product of two self-reciprocal is reciprocal. The product of two skew reciprocal is self-reciprocal, and vice versa. Product of self-reciprocal and skew, or skew and self, is skew reciprocal. This gives us a way to prove the important statement. The sets R and RS exhibit and the multiplicative commutative monoid such that R is a quotient of the RS over zeta 2. So they behaves like the integer number and the even number. I would like to explain it in such a way. So factorization of self-dual symmetric polynomials. it's very important, and I will show you now why. So self-dual polynomials we will call reducible in RS if they can be represented as the products in such or another way. Otherwise, they are called irreducible. And here are several statements. First one is let a self-dual be reducible in RS such that the inequality holds with one of the is coincides with one of these four, or one or two or three or four, then necessarily unimodality numbers satisfy the following equality: the sum of two multipliers, sum of unimodality numbers of two multipliers is equal to unimodality number of this product. And moreover, let a self-dual polynomial be given if for any pair of self-dual polynomials 1 and 2 holds the following, then a polynomial h is irreducible in RS. Let us fix n equal 2 and consider the skew reciprocal polynomial s. And here comes a very important statement that this polynomial is always reducible. It's always reducible means that does not depend of m. We can always find the divisor, and divisor is very nice, lambda square minus x1 x2 that divide this polynomial. This is why, I'm sorry, this is why the Keller duality relation has the unique solution lambda is equal square root of x1 x2, and in physics means it does not depend on any kind of the tessellation. What is important, there has to be exchange variable and piecewise. I mean 50% of this black and 50% of the white. And this is only unique case when you have the, sorry, here it's correspond to the fact that the unimodality number of the skew reciprocal polynomial is 0. It means it has not any freedom, I would like to say. Now, sorry. Yeah, we are here now. Yeah, and generic self-reciprocal polynomial with m is larger than 2 are always irreducible, and the same is for the R self-dual with n equal 2 and irreducible in this case of n larger than 3 in S. Here in this section, I will tell you why, what is the goal to study such kind of polynomial, and especially the skew reciprocal. The skew, let us look on this root of skew reciprocal polynomial. The root lost its universality. I mean that because of the unimodality number is always larger than 0, it depends of different coefficient, but something is generic. So first proposition, symmetry or homogeneity. Lambda xn be a real solution of skew reciprocal equation. Then it is invariant under the action of symmetric group. It is understandable because we go to build this equation with this invariant, and moreover, it is homogeneous function of the first degree. Duality. the root of this equation, skew reciprocal equation, satisfies the duality relation. I mean the equation 2 in the first page. The second one, compatibility. The root of the skew reciprocal equation compatible with, I mean, if all x1, x2, and so on up to xn are equal, so lambda is also x. In physics, you can see if all constituents are the same, so the average is also the same. There are some cases when we can find exact solution. Positiveness. If all these coefficients that are going into this equation, skew reciprocal, are non-negative, so the unique equation is also non-negative. And the last one is monotony. Monotony means that all the first derivatives in xi are positive. I have called such lambda perfect function if they possess the following properties: positiveness, invariance under the action of symmetric group by permutation, homogeneity of the first degree, self-duality, compatibility, monotony. Let us look, we go to require one more point that is very important. I will call it proper self-dual polynomial. Consider self-dual polynomial without middle term. They have two different parts. One of them I take away from these brackets, and I came to the representation of skew and self-reciprocal polynomial in the following way. And this is the theta, the capital theta, and gamma is the product of the ratios of the invariant. And now, the theta satisfies the duality relation. All is very nice. And now we will use known results of the Hardy-Littlewood polia in this book as inequalities. Let A1 up to the n, B1 up to Bn are non-negative numbers. Then the product of two invariants satisfies the equality. If and only if satisfy several inequalities, also can. Applying the Hardy-Littlewood polia to our case, we can prove that if some very, very mild relation to this degrees are satisfied, so gamma is bounded by the E1 at the arithmetic sum over in the here are the different gamma. They are satisfied, the first three, and the last one does not satisfy. Important property of the solution is the following: lambda be a real solution of the proper skew reciprocal equation is bounded by the harmonic and the arithmetic part. And by the way, the proper self-dual polynomial does not exhibit the commutative monoid, but this is not very important. What is much more important that we can improve very strongly the bounds, and in the case 3 and 4, we arrive to the following bounds that are much more stronger than before: the omega small and omega capital here and here also. Because the lower degrees has much more opportunity to make the bounds much stronger. The conclusion is, for the larger M, the solution is not universal, but the bounds are universal. The open problem: to extend the self-dual multivariate to be invariant under the action of the finite subgroup of Sn. To look the convergence pointwise uniform on some else for the infinite sequence of the perfect algebraic function. Here, the thought is not the conjecture. I am scared to put the conjecture, but I strongly believe that all the perfect functions that are satisfying the duality relation, that are invariant at the Sn, that are positive, that are monic, and so on, so are algebraic. To extend the bounds for the n more than 4, and conjecture 1 has to be proved. Thank you very much for your attention.
Thank you, Leonid. So thank you very much. I think because we're running a little bit late,